Hey, this is Leach with Simpson Math, and in this video, I'm going to be going over a linear regression problem. We're going to talk about how we can find the slope, the y-intercept, go ahead and talk about r, show you where r squared comes from as well, and then talk about residuals, how we can over and underestimate, and all that stuff. I'm going to do it in Desmos, Excel, and in the 83. I have my correlation does not imply causation t-shirt on, so let's get started. So I'm going to focus first on the Desmos aspect because it's nice and visual, and then I'll go through the Excel and the 84 part. So this is data from a small bookstore are shown in the accompanying table. The manager wants to predict the sales from the number of salespeople working, and we'll complete these parts. So let's take a look at the table. It says we have number of salespeople working, 2, 3, 6, 9, yada, yada, yada. Sales 11, 12, 13, 14. Now that's not $11, $12, that's 11,000, 12,000. So always be careful about our units. So these are paired data. This data is not just sorted arbitrarily. This 2 is stuck and tacked on that 11. This 3 is with that 12. That means when there were 2 salespeople working on some particular day, that there was $11,000 in sales, and obviously they're rounding to a nice even number. When there were 3 people working, there was $12,000 in sales. 16 people working, $22,000 in sales, and so forth. They do at the bottom give us x bar, y bar. That's the mean of the x's, the mean of the y's, respectively, and the standard deviation of the x's and y's. If they gave us r, then I would be able to use formulas without even really having to go into technology and determine the slope and the y-intercept of our function. Of our least squares regression line. But they didn't, so I'm just going to have to use technology anyway, but I will model just those formulas just in case, just for kind of completeness of this video. All right, so to get this over into Desmos from a MyLab question, just click on the open in whatever, and I'm going to do the copy to clipboard. So copy to clipboard, and then I will be doing tab, not comma separated. If you do commas, it's not going to move right into Desmos. Stick with tab and it will work. So Control C, Control or Command C, or right click copy. I'm going to hop over to Desmos, and I'm going to just in an empty row, just paste in, just press paste, Control V. When I do, it does a few things. One, it moves my window around. Let me scooch that over just a bit. There we go. It moves my my window around, so that way it is zooming in on my data. How nice of them. It will then also just format that 2 is with the 11, 3 is with the 12, so forth. It does get rid of the headings. If we look back at the copy to clipboard, notice that the X bar, Y bar stuff at the bottom was not an option, was not available to be copied, and the header was just ignored by Desmos. So it was like, oh, those are words, let me not worry about them. So that's good to know. So just copy and paste, it moves it over. How about that? If for some reason you're zoomed in weird and you can't see things, remember there's the zoom bit right here. You can click and it will zoom it. My screen is scrunched a little bit, so it's just a little bit small. If you want to make the dots bigger, you can always press and hold and then edit this. I can make those dots be just a bit bigger so you can see them a little bit clearer. All right, so now let's talk about getting the regression line. So do note that our x and y values are x1, y1. Those subscripts are important. It's been a while since I played with them. If you delete one or both of the x1, the subscripts, it kind of gets angry. So just leave them. It'll be fine. It's real easy to deal with. So before we start asking Desmos to make the least squares regression line, we need to talk about what's right above me is what is the least squares regression line formula. So you should remember from like your algebra days, y equals mx plus b. It's the same process, same basic thing. We're just putting some extra symbols on it. So that b for the y-intercept or these coefficients, we're going to be stealing and kind of using that. But do note that the b was our y-intercept. There's no x on that b. So actually in stats world, we like to have the y-intercept be first. And then let me get that back from my disappearing ink. And then this mx, the m is the slope, the x is the independent variable, and so that's what's happening here. b1 is slope, and then x is that variable. So let's talk a little bit about that and why we have this. So first up, we have y hat. Y hat is the predicted y. So notice that my actual y's are 11, 12, 13, 14. When I input 2, 12 pops out. Sorry, 11 pops out. When I input 3, 12 pops out. Those are the actual y. When I get done with this, I could make a prediction of, well, we saw one time when 2 happened, 11 came out. Notice at 10, we have two different 10s. One time when 10 happened, we had 19,000. One time when we had 10 workers, we had 21,000. So what do we expect on average to happen with 2? Well, that's what would happen. That would be the output for that would be the hat. Or maybe I want to predict how much revenue we would have, or there's total sales money, how much our total sales would be. If there's 4 workers or 5 workers, that's not in my data set, but that would be appropriate X to use to predict. So that's my predicted, not an actual Y. Then, as I just pointed out, the y-intercept is the one without the variable, and we do like to write it first. And then here's our slope, and then the independent x. Why do we have it like this? We're not just trying to be difficult. I'm setting the stage for future stat classes. So future U takes a stat class that does multiple regression. We won't cover that in my business stats or regular stats class. But if future U takes a course with multiple regression in it, it would look something like this. So you know how this is B1? I would also stick a 1 onto the x. And then I could say plus B2 x2, and then B3 x3, and B5 x5, whatever, yada, 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 to however many x's. In this particular case, this is the number of workers. Maybe this additional x variable were the number of customers. Maybe I want to use the number of customers to also help predict how much revenue there's going to be. So if I have a way of documenting the number of customers that come in through the front door on a certain day, then I could use that to also maybe make some predictions. And so that's an example of how I can have two x independent variables to predict that one output. But in this course, we're not going to worry about that. We're just setting the stage. So that's why we have the x after the x in the slope after the y-intercept. All right, so you already see what it's going to equal down below. So let's get there. So in Desmos, I basically need to type in this equation, and I'm going to, the only change I'm going to make is I don't include the hat, and we're going to be using a tilde for it being similar to, and then we of course will have the 1s after the y and the x. So let's do that. So I'm going to type in y1. I have to do y sub 1 because that's what Desmos knows my y values are. So I'm going to type y1. To do that, I'm just going to press a keyboard twice, y1, and it will automatically subscript. So if you type in a number directly after a variable, it subscripts. If I do it before, it's just 1y. But if I do y1, it'll auto subscript. If you wanted to know how to forcefully subscript, you do underscore, so shift dash, or if I'm going to open my on-screen keyboard, it is under the z and the x, this a sub b. That's how you can forcefully get the underscore, or forcefully get the subscript. And then in a second, I'm about to do a tilde for similar to, and if you want the on-screen keyboard, it would be there. All right, so now let's do that tilde. So I'm just going to press shift and then tilde. It's the above the tab, left of the 1, or use that on-screen keyboard. If you did that twice, it would be approximately equal to, but we want similar to or being modeled by. So in stats world, we just use that 1, and that's how Desmos wants it. All right, now I'm going to type in b0 plus b1 times x1. So b, and then to get the subscript, just press the 0. Do note that it's trying to help us out and model this data based on this, but the x isn't there yet, so it doesn't really know what to do. It's not really giving us helpful information. So just ignore it. b0 plus b1, so again, subscript, just type the 1 after the b. And then now I need x1. Again, I'm picking x1 because that's my input. My input, Desmos knows it as x1, so x1. When I do, it's in red today. So that is our slope, or sorry, our regression line here, fitting through that data. Notice now it's saying, B0 is 9.26923. The B1 is 0.873077. and then it even gives us r and r squared. R is the correlation coefficient. Remember, that is a measurement of strength. The closer that is to 1 or -1, the stronger the relationship is. Then the closer it gets to 0, the weaker it is. Typically things between like absolute value of 0 and 0.5 we would call weak. Between the absolute values of 0.6 and 0.7 we kind of call moderate. 0.8-ish to 0.9 we start calling it strong. And notice I wasn't exclusive in all those gaps because it's kind of a little bit interpretive. Bigger than 0.9 we can start calling it very strong. This one I might just call rather strong. So just kind of some loose intervals there, but this is a pretty strong R, pretty strong linear relationship between these two variables. All right. So when we write this down as our regression, it looks like this. So I'm going to do sales hat. So I'm going to summarize, abbreviate the y variable by name, and then stick a hat on it. So that way it is sales hat. It's the predicted sales. This rounding to 3 decimal places is the y-intercept. And then rounding to 3 decimal places, here is the slope, that's our B1. And then writing our x value, some summary for that, our number workers or number of workers, so forth. Right, so that's how we can write our equation there. What do I have next? All right, I want to talk about how if for some reason we either weren't given the data, all the data values, we were only given the summary statistics including R. So if they only gave us x bar, y bar, s of x, standard deviation of x, standard deviation of y, but then they also gave us R. They also defined the relationship, the correlation coefficient between x and y, the linear relationship. I would be able to get the slope and y-intercept just by some simple algebra using two formulas. So let's talk about those formulas. Again, I don't need to find these because I just had technology, but let's process and see how this works. So the slope formula is defined by B1 equals R times SY over SX. Let's process that for a second. So first, notice this is SY over SX. Oh, SY is the standard deviation of the Y. So what my lab was calling SD of Y, I'm just calling it S sub Y for standard deviation of the Y's. So we have our standard deviation of the y's divided by standard deviation of the x's. So think about this. This is the change in my y's, how much y's vary over how much my x vary. That is literally rise over run, that slope. How much my y's vary divided by how much my x's vary, the rise over run, that is slope. If r was 1, then slope would just be that ratio of standard deviation of y divided by the standard deviation of x, that rise over run. But because this is not a perfect linear relationship, we have a little bit of a regression to the means. So we have the Pearson correlation coefficient, this r, and we kind of have a bit of a penalty that we have to pay, and it kind of makes it a little bit less steep as a result with that little bit of a regression to the means as a result, and so that kind of in a way kind of weakens that slope there. So we have to adjust it based on R. All right. Then also just one more thing, if you know how R is calculated, which is a whole other video entirely, but if I was to standardize the standardize my y's and standardize my x's, so remember, if I were to standardize my y's, the standard deviation of z, of any z, is 1. So if I standardize my y's, this is a 1. If I standardize my x's, this is a 1. So when I'm talking about standardized values, the slope is literally just r from that formula. All right, now how would I get the slope, or how would I get the y-intercept? Well, here's how. So again, I have y equals mx plus b, just as a reminder, but it did switch the mx and the b, so our our y-intercept is first. Let me put it in our stat form. So there's our y hat, b null, b1, and our x. A fact about the least squares regression line, which is the line of best fit we're using, it passes through the point x bar comma y bar. It will always pass through that point. So I'm going to substitute in x bar for x and y bar for y, for the y hat. And then lastly, or next, rather, notice I can find slope from standard deviations and R. So I'm going to take that slope that we just found and plug it in. So if I did that, notice I have 3 of our 4 things known. I have them colored in a different color. We know what they are. So I can now solve for b sub 0, the y-intercept. So subtract b1 x bar from both sides. And I get this. X bar minus b1 x bar. Sorry, I might have misspoken. Y bar minus b1 x bar equals our b null. Or when we write the b null first, it's b null equals y bar minus b1 x bar. So if we take our values here, which these values were given to us on the on MyLab, and then we just found R, or we could calculate it. So I could do mean of x1. So from your previous studies from single variable quantitative data, I just type an MEAN or do the function mean, and it does mean open parentheses. But I do need to do x1 because it doesn't know what just x is. So I do type in x1 and I get my 10. If this was a y1, I would get 18. And then for my standard deviation, STDEV. Since it's standard deviation of a sample, it's just going to be the regular standard deviation. So standard deviation of x1 is this 5.37 with a whole lot more other decimal places. And then y1 is 5.01 with, again, a lot more decimal places. All right, so that means that if I want to calculate this, if I want to calculate rather the slope, I just need to plug in, sorry, let me zoom out. I just need to plug in the, I have this formula right here, B1 equals R times SY over SX. So I'm going to grab my R, I'm going to grab my SX, and I'm sorry, SY and my SX and plug in. So this is R SY over SX. Let's plug it in and verify that we get 0.873. So 0.9365 times 5.01 over 5.37. That's as accurate as we got on the other page. So notice out to at least a few decimal places, 2 to 3 decimal places, we have that same amount of accuracy using the same amount of kind of digits that we have available to us. We have 3 digits of accuracy, so we're able to be kind of 3 digits of accuracy here. This one's 4, but at most we have is at 3. If I find more accurate values, I of course would use that, and I would get a more accurate slope. Then to find our y-intercept here, again we're going to use our formula. This time to find this, I need y bar, b1, and x bar. Well, I just found b1, so I'm going to use that, and y bar is 18 and x bar is 10. So I'm going to plug in. Here's my y bar, the slope, the x bar, plug it in, and we should get 9.269-ish. So 18 minus 0.873 times 10. And I do get 9.27. Notice that it should be 9.26923. Well, that's because a little bit of for decimal places. If I used more decimal places within my slope here, so if I put in 0.873077, so notice when I start typing in numbers, I'm getting more and more accurate data, more and more accurate values here. There's a better reflection of that. So it's always better to use more decimal places. So I wish they gave us a little bit bigger numbers, or of course we could find them ourselves. All right. So let's take a look at how we can, let's take a look at how we can input these questions into here. So it says find the slope estimate. That's our 0.873. So we got that 0.873. Now, what does this mean? Now, I do want to point out that our slope, rather our y value, remember it's in thousands of dollars. So when the slope here is 0.873, we actually need to do a little bit of a conversion here. So first, if I look at it this way, this is 0.873. The slope is actually, I kind of have that wrong here for a second. it's in thousands of dollars per one person. So let me scooch this times 1,000 over in a second. So this is in thousands of dollars. Oops, actually, I'll just do this. So do you agree that if I take any number, if I don't know what it's over 1. If I don't see the denominator, it's over 1, even if it has that decimal, right? So this numerator value is thousands of dollars over the number of workers. Right? It's rise, slope is rise over run. And in our data value here, our y value is is sales, x value is number of workers. So it's the change in y over the change in x. So the rise is dollars, run of workers. Now, I'm going to multiply this numerator here, or multiply this whole thing by 1,000, so that way I can get it to real dollars, because this is in thousands of dollars. And when I multiply this by 1,000, I then get 873. So instead of thousands of dollars, it's just $873 for every one worker. So if we put this sentence together, I personally like to work from my x value. For every one additional x value, we expect our slope amount of y value. So let me put the context in there. So for every one additional worker, we expect, or the model predicts, $873 additional dollars of sales. MyLab here has it a little bit different. It says an additional $873 of sales is associated with each additional salesperson. They didn't say the one, but it's implied salesperson, that it's one person, one worker. This word associated here is important because it's what I call the fudgy word. If you were paying attention to what I said a second ago, I said for every one additional worker, the model predicts an increase of $873 on average. So the predicts, so that on average is a little bit of a fudginess because it needs to be non-deterministic. It is not when I add one worker, it will go up $873. That is like a kind of a causation thing, which that is not what's happening here. I cannot be like, well, I'm just going to add another worker and I will make $873 more today. Nope, it does not work that way. All right, so then find the y-intercept. It's wanting it in just the regular number, so 9.269. Now it's wanting me to convert it to the nearest dollar. So it says nearest dollar. This other did say nearest dollar. Almighty blue text tells us what to do. So we can multiply by 1,000 and we get 9,269. Now, which of these is the thing? So when I take a look at my graph here, I see that this line is crossing through the x-axis at 9.269. Now, does that make sense? What's my x? My x is the number of workers. The y is the revenue, or rather the sales. So if 0 people are working, I expect $9,269. For 2 reasons that doesn't make sense. One, that's just bonkers. I can't have a bookstore with no employees. Even in today's day and age with self-checkout, that's just not going to happen. We're not going to make $9,000 with no employees in there. And then the other thing is, it's beyond the scope of our data. Our data goes from 2 to 19. So I noticed from 2 to 19, it looks pretty linear. I don't know what's happening before 2 or after 19. So I don't really feel comfortable making predictions beyond this kind of window here. So that's why this says that it's kind of not meaningful. So it says on average, $9,269 is expected when 0 salespeople are working, which notice that's A and D, but this is not meaningful because it doesn't really make sense in this context. All right, then E is just to write down our equation, which our line of best fit, which we already did. So now it says if 18 people are working, what sales do you predict? All right, let's do that. So I'm going to pop over to Desmos. And I'm just going to take sales hat equals 9.269 plus our slope. And then instead of workers, I'm going to put in 18. So 9.269 plus the 0.873 and then times 18, because I'm replacing the number of workers with an actual number of workers that we're looking at, which is 18. So then when I do that, I get 24.983 in terms of dollars. That's $24,983. So that's why we get this number, 24,983. Now, I have 3. This says 5. Just a reminder about MyLab. As a student, you might not see multiple acceptable answers, but from my teacher vision, I do see that they'd be fine with a default 24,985, 24,983, or any of these numbers in between here. In fact, any of these are good with and they even have an answer tolerance of plus or minus 47, just because they know there's some kind of potential rounding errors that are possible out there. I suspect, I haven't figured it out, but I bet the 24,985 would be, if I had more decimal places for y-intercept and slope available to me, if I used more decimal places, then I bet this 985 would come out instead of the 983. But using these 3 decimal places, the 983 comes out. Cool. So this question admittedly is a little bit poorly worded, but F and G are together, or kind of glued together. If 18 people are working, what cells do you predict? Keep going. If those 18 people are working, if cells are actually 24,000, what is the value of the residual? So let's talk about residuals for a second. If you notice, this is the last part of this problem. So here this is not the graph that we're looking at here. This is just a dummy graph. So here I have an XY, I have 4 data values, 1, 2, 3, 4, and I've pretended to fit this line of best fit that goes through there. All right, I'm about to make it a little bit messy and add some things to that. Just wanted you to see the clean version. All right, so let's talk about what are residuals. So first up, if you want to abbreviate residual with a single value, with just a single letter for a symbol, we're going to use the letter E. E for error. We aren't using R for residual because R is exclusively saved for Pearson's correlation coefficient R, which I think has something more to do with just kind of the idea of the regression. So that kind of takes precedent over the residual. So we're using E for error. So use E, do not use R. Next, what the heck is E? Just like how I define deviation, because that's basically what this is, kind of what this is. Deviation, my default value is observed minus expected. I like to start with that because this observed minus expected, O minus E, shows up throughout the course. This is what I observed, but this is what I expected. I didn't get what I was expecting. Is that weird? That's kind of the crux of this course. So observed minus expected. Back in standard deviation, when you learned about deviations, it ended up being the observed data value minus the mean. Well, today, it's not. Today, our observed is the observed y value minus what are we predicting? We're predicting y hat. So it's still observed minus expected, but we're doing y minus y bar. So let's talk a little bit about one of 2 possibilities here with our residuals. So suppose I have some x, and this x, x value, actual x value is this y right here. So let me put in a x right here. So if I had an x here, then this data point would be x comma y, some observed x comma some observed y. But then there's a predicted data value for that x, and I can call that x comma y hat. When I plug in an x, a y hat pops out. So this x leads me to an actual y and then an observed y. So if you look over on the on the y-axis, you can see this was my observed y. It's bigger than my predicted y. So there's my y, there's my y hat. So when I do my residual, I'm going to do my y minus y hat, which is a big value minus a small value. So what do I mean by big minus small? We'll just look on the y-axis. Remember, this would be 0 on the y-axis, negative numbers on the y-axis. So the further up I go, I have bigger numbers. So this y is bigger than this. So I'm doing some bigger number minus some smaller number. Don't stress about what they are. My iPad is trying to spell check for me. Sure. That's less clear. I have some big number minus a small number. Well, if I do a big number minus a small number, I'm going to get a positive number. So I'm going to have a positive residual. All right, I'm going to come back to the estimate part in a second. Let's take a look at this other one. So here, if I have this x, this other x, oops, that's the thick pin. I have this x, well then I have an observed x comma y, but then I have a predicted, in this case, x comma y hat, all right? So I have a y value, an actual observed y value of y, a predicted y value of y hat. So this residual is going to be y minus y hat, same thing as before, but now my y is smaller than my y hat. So I have a small data value minus a bigger data, or small value minus a big value, which can produce a negative residual. So these residuals are the distance and direction. The y value is in relationship to its predicted value, distance and direction, just like our deviations are. So let's talk about over or underestimating. Actually, sorry, before that. So the positive and negative, since we were just talking about the negative one, notice this is from the point of view of the line. So the residual itself is from the perspective of the line, of the predicted line. So if I'm standing on y hat, I go, oh, look at me, I'm standing on this y hat. Ooh, I'm having to look down on this actual observed value. That observed value is so much smaller than me. Looking down, that's why we have this negative, a negative residual. All right. If I come back up here to the positive residual, if I'm standing on the predicted line, I'm having to look up to the actual value. So notice that we have a positive residual there. Now let's talk about the over or underestimate. This over or underestimate is from the point of view of the data value, the real data value. So now if I'm from the point of view of the POV of the real data value, if I'm standing on the real data value, I go, well, in reality, I'm standing on reality. My prediction, oof, that prediction was below me. That is an underestimate. That prediction here did not reach up to where I actually am. So that is an underestimate. Compared to, sorry, kind of going all over the place. Compared to here, again, standing on a real data value from the perspective of this, the line is my estimate. So I'm looking for my line in relation to reality. This is an overestimate. I'm having to look up to look for that, to look for the predicted line. So this is an overestimate. They do kind of feel backward. Negative residuals are then overestimate. And the reason for that, they surface level might feel backwards, but when you look at it, it's because they have different POVs, they have different point of views. So for this question, I need to find the residual of 18 cells, of 18 people. So if 18 people are working, we predicted $24,985. Well, we actually got 83, but I'm using the 85 here. Then we said, oh, but what if you actually observed, what if there really was just 24,000? Well, observed minus expected, we get a negative 985. Just a reminder that whatever you use here, it should give you that same amount of tolerance between that. So we have the same options about a wiggle room. So don't stress about questions leading into each other. MyLab should have taken care of that already. All right, so if we have a negative residual, I'm in this situation down here. So I know 18 isn't really this early in the question, but if 18 is about here, so that's our 18 in this particular case, just because I have the residual picture is matching. So this is my 18. This is the 24,000 is the actual number. The model was predicting 24,985. So then when I do that subtraction, I'm getting a negative distance again, because this negative is from the perspective of the prediction line is looking down at reality. But in terms of where is my estimate compared to reality, it's an overestimate. So this last question is that this is an overestimate. All right. So that's this full question, and I did it all in Desmos, and I did a whole lot of yammering just for kind of teachery things. I'm now going to show you how to do this in Excel and then in the 84. And I'll go quickly just to demonstrate that tech instead of having to do the kind of a teach with it. So if I click the icon, I can click my options here, and then one of them is to open in Excel. I've already done that. It would download and opens up and it gets something like this. All right, so this I've made. I'll walk you through it. So I've just zoomed in on my number of salespeople working and my sales. There are other more fancy ways. I'm doing kind of just a direct approach to just directly get the functions we want. There's one way you can use the data analysis tool pack. Oh, you don't see that, but you go to data, and if you have the data analysis tool pack turned on, you could use that. I'm showing you just how to use the native built-in functions. So you should see over here, I have printed the functions so that way you can see what these are. Let me just bulb them up so we can see them a little bit better. So these are what is in this box. So this is intercept of this stuff, but you can see what those are. Okay, so for my y-intercept, if I double click on this, notice it's the intercept of my known y's. It might be a little bit small here, but the tooltip is that it's wants known y's, comma, known x's. It does want the y's first. It does, the slope in y-intercept does matter which one's x and y. So make sure to answer that correctly. So the y's first and the x. Just to demonstrate once, if I want to intercept, I'm going to say equal to int. Oh, intercept is that second one down. I'm just going to arrow down, press tab. Known y's, I'm going to highlight my known y's without the heading, comma, known x's, highlight my known x's. They have to be the same size. If I highlight all the way down here, it's going to yell at me. So they need to be the same size. You can close the parentheses or just go ahead and hit enter because we're at the end of the required elements. And that's where I get that y-intercept. I'm going to go ahead and delete that because I don't want it. All right. So then similarly, all of these are known y's, comma, known x's, except for the correlation, which is just array 1 or array 2, because remember, correlation doesn't matter about x and y's. If you interchange x and y, you get the same thing. So slope is a similar thing. Slope of x's and y's, sorry, rather y's than x's. R is not just R, it is correlation. Remember, R's full name is the Pearson correlation coefficient. So that's why it's a correlation. If you start looking it up, it should then tell you, like if you do equal to correl, returns a correlation coefficients between the two data sets. Two ways to get R squared, which will, this thing won't that go away. Two ways to get R squared. It's literally R squared. You found R, square R. That's it. So I've just grabbed this and said square the thing. Or there is the function rsq for R, sq for square, R squared, straightforward. This does have known y's, known x's, but it shouldn't matter if you switch them around because it's the same thing. Now, lastly, to do the math to get your predicted. So if I plug in an x, I want to get plug in the 18. What do I get out? So I just have two inputs. And when I'm making, me personally, when I'm making kind of an Excel calculator, I like to put like a yellow or something like that where this is an available input. So I need to put something in there for other things to work. Can maybe do some other color coding to help you out. But that's one that I've kind of stuck with and I really like. So if I have this program in so that if I put in the 18 for the x, watch this y hat, the y hat will update to that correct value, 24.985. But I want to end up doing the, I'll multiply it by 1,000 to get the 24,000. Notice it is 985 because this is more accurate because this is using all the decimal places of slope and y-intercept that are calculated. Now, how did I do that? You can see it over here to the side, but let me color code it for us. So I'm just taking the function. I'm taking the y-intercept plus slope times the x. So I know the y-intercept, I know the slope, I found them up above, and it's using these things. And then I just have this little input here. You might be, sorry, just inspiration struck me. My question is, can I get intercept of all the b's, comma, all the a's, and will it ignore those things? Yeah, it'll do that. So that's a nice option that you could do. I could change that to be, let me scooch this down so you can see this. What I'm doing here is just did all the whole column of B, comma, the whole column of A. Why might this be helpful? Well, because if I were to add, let's say, 25 and 32, for another pair here. Notice these then update. This is updating correctly, but this is still stuck at this one. So you can do that whole column to be able to be a little bit more flexible, or you could just kind of copy and paste the table in, and if it's just a little bit or a lot, if it's just a few lines or a whole lot of lines, then it will update automatically. That's kind of a little bit slicker. Just do the whole column. Does slope do the same? Just trying things out on the fly. Slope. Yep. So it's ignoring the words. It knows that that's text. It's ignoring that. Does R do it? Or sorry, Corel. C-O-R-E-L. Yep. And I bet RSQ does as well. Oh, well, I do a W. That's one way for it to not work. Yep, so that works. Cool. I'm going to delete that so we don't have that confusion there. But so that's a nice kind of flexibility way for your calculator to be a little bit more green. Evergreen, I think I meant to say. All right, so now we need to know if we know a y value, if I know an actual y. So notice my output here is my y hat that I was interested in. I want to know my residual. So if I know my actual y, which was 24,000, oops, I should put in the 24 because it's still in tens of thousands of dollars. So this is doing just simple subtraction. My observed minus expected, known y minus y hat. And that's how I get my residual there. Again, move it over through decimal places for the thousands of dollars. All right, lastly, let's do the 84. So let me turn the calculator on. Press it harder. There we go. Then I'm going to go to Stat, Edit to type in my data. Past Leach, thank you for typing it in. Just type in the list 236. I'm just press Enter between every number. Arrow over and then press it down, then 11 enter, 12 enter, 13 enter, on down. As a tip, general tip, when you get to your last row, I have 10 numbers. I know I have 10 numbers. And so I'm just going to make sure that you see how this is L210. Oh, I can get a bigger screen. There we go. You see how this is L210? That's a nice way for it to count to know that those are the same and those better line up. So either I missed one in each, if this was, I could have messed up. There's lots of ways that this could mess up, but this is at least a nice check that I have 10 in this column, 10 in that column. Might be fine. Quick look through, I don't see any mistypings. So I'm now going to press second quit to go back to the calculator screen. Now I'm going to press go back to stat. This time over to calculate. Sorry, pardon me, calculate. You could do number 4. That's the more algebra type approach. That's more of an mx plus b, but it has an a instead of an m. But we're going to do the linreg a plus bx. So instead of an a, it's actually b null plus b1 x. But a will be the y-intercept, b will be the slope. So choose that. It defaults to L1, L2, which are the ones that we want. For some reason, they were not in L1 or L2, and they were in the others through L3 through L6. Then you could press second those numbers to update those. We really just need to do calculate, but I do want to show you how you can make the scatter plot quickly on here. So if you wanted to store this equation, this regression line, we could store it into the y1. So I'm going to press, this is super duper optional. I'm going to press vars. Vars is short for variables, not variants. These are variables. So vars, I want a y variable, so I'm going to arrow over to y variable. These are some of the different types of y variables we could have. So I'm going to do a function y variable, and I'm going to pick y1. So what this will do is this will just copy and paste the entire equation with a whole bunch of decimal places into y1 for me. So I'm going to press calculate. If for some reason you don't have r or r squared right here, then you don't have your stat diagnostics turned on. So if you go to mode, I have it right here at stat. Let me just go down. Stat diagnostics on. For some reason, by default, even in 2024, it's set to off. Don't know why. The stat wizards are on by default. That's great. But the stat diagnostics are turned off. So so just turn them on. if you didn't see r and r squared, and then rerun it, or secret, just arrow up, and then rerun your last enter, arrow up twice, and then rerun it. All right, so notice same numbers that we've been getting, yay us. Now I promise I can show you how to graph it. If you press y equals, it's already typed in there for us because I told it to do so with a whole lot of decimal places. Lucky us. So if you just press graph, you're going to see the line because it at least does cross through somewhere in the -10 to 10 window. But I want to see my dots. I don't see my dots here. Well, the first dot is 211. So it would be like on the big window here, it'd be at over 2. Up 11 is the first dot right about here. So I could manually adjust the window, but really I'm going to press zoom and then go down to number 9. You could just press zoom 9 or do zoom stat. And that's going to zoom into my active statistics, which might not be active. I need to turn that on. That's why. So I'm going to go to press second y equals. You see how that is stat plot. I need to turn on a plot. So it doesn't matter which one. You can basically you can make 3 plots. You can have 3 different graphs going at the same time. I just need one. So I'm going to turn on number 1. Press on. Pick the type of graph you want. The first type is the scatter plot. So let's have that one be selected. Notice you could do box plot with or without outliers. You could do a histogram right here. L1, L2, that's where our data values live. Let's leave that. You could pick what type of mark you want. If you want it to be an open dot plus a big dot, a small dot, we'll just leave it at the open dot. No need to stress. And it will color it blue. Sure. So with it being on, I don't need to say go. With an on, it will now actually, it knows that there's stats. So if I press zoom 9, it's going to now zoom into my dots and then graph the line around it. If for some reason you want to be cute, if you have a color screen, second y equals, and you wanted to change that color so that the dots are different color than the line, you could change the color to, there's red, so now I'm going to do zoom 9. They're my red dots, and then here's the blue, the squares regression line. If you want to kind of touch the dots a little bit, you can press the trace button, this one, and then just arrow left and right, and I'm jumping around the scatter plot in the order in which you typed it in, I think. And if I press the up or down arrow, it should move to the equation so I can trace along that line to kind of get a little bit of values there. Alrighty. So I think that's enough. So in here we covered how to find a least squares regression line from technology using Desmos, Excel, and the 84. We talked about how to find it using the formula if you're given the means, the standard deviations, and R. And we also talked about residuals and residuals, and then interpreting slope and y-intercept. So I hope this part helps for you. If you need more help for more regression and correlation stuff, check me out on some of my other videos. If you're in my current sets right now, just a second, I'll get a few more recorded and I'll get them up shortly. All right, take care, and I'll see y'all in the next one. Bye.